without further ado, I would like to welcome him to the stage.
I'm now wired, so I think you can hear me, right? So, well, I would like to start, like everyone else, by thanking the SIS and the organizing committee for inviting me to come here. First time, the south part of India is fascinating. I flew in last night at 1 o'clock. So I'm really looking forward to the conference and interacting with all of you. Thank you, Chandra, for the nice introduction. I will not talk about your work here today, because I knew that you're going to be here. So we'll talk about something else. And this something else started with a conversation in my lab with a couple of PhD students and postdocs right before the pandemic, a few years before the pandemic, where we talked about manipulating nano objects, in particular biological nano objects, but at the individual object level. That is, can I have devices that I can pick one and just look at it, study it, one by one. And that is the reason for the word quantum in my talk. So there will be no quantum mechanics. So quantum means at the individual level of these nano particles. And what is quantum in biological nanoparticles? I mean, we talked about it. We said, well, a virus maybe, but really we were targeting molecules. So a biomolecule will be the biological quantum that we will be targeting. And the first part of the talk will be then and it's responsible for the word valving, will be to tell you where this travel has taken us over the past 2 years. The second part of the talk is pretty much the same target, but with a different technology, that of printing, where we've worked for many years. And then I will report to you where we are in terms of printing at that same quantum level. So, and I think a slide like this can be very easily appreciated by this audience, because you see here a cell, that's 5 microns, let's say 20 microns. You see a bacterium, a few microns. And then you go down to the nanoscale, you see viruses or nanoparticles. And then you go down to quantum dots and molecules. So in this talk, we're interested in this category of particles, dealing with biological nanoparticles and other particles, not only biological, but also other particles, down to molecules. And the talk, like I said, has 2 parts. The first part has to do with valving. And we'll discuss in a second what valving is. It's a verb. We're more familiar with the noun version of this, which is a valve, right? And the second part is printing. The 2 parts have a common sort of denominator, and that is electric fields. We will use electric fields to do what we do in combination with things, okay? In the first part, the electric fields will be working collaboratively with a sort of rational nanotopography that we will put in our devices, so we can do what we want. And in the second part, the electric fields will work collaboratively with interfacial energy of liquids, again, to lead us to where we want to go. And let us start then at the beginning by all agreeing on what a valve is, right? So a valve is everywhere, in all devices in the human body, everywhere, wherever you want. It's a fantastic device, very much unappreciated, because we have it, we use it, we never really thank it for what it does. And according to Wikipedia, it's a device that regulates, directs, and controls the flow of a fluid by opening, closing, or partially obstructing various passageways. So then we'll try to do that at the quantum level. And a typical valve most valves are mechanical, in that they have a diaphragm that you could screw down and move up, and then the fluid can go through the pipe or not. And then if you look at the history of valves, now I would love to sit down here and tell you the first valve was invented in India, but it was not. It was not even invented in Greece, all right? So it was actually attributed to the Romans. And the principle was that of a plug valve. So basically you have a channel, and then you plug the thing in. The plug has an opening, as you can see here, the more modern manifestation of this. You turn it, and if the opening is aligned by the flow flows through, or you can close it, okay? So that's the principle. And then over the years, various luminaries of science and technology have devised different valves. I'm not going to have an attempt to explain to you Da Vinci's design of an underwater valve. Right? So one that allows you to go underwater and it closes based on the pressure of water and so on and so forth for diving. Of course, science has changed since then, and we fast forward to like 10 or 4, is that 20 years ago, like 2,000 years forward, all right? And then we see valves in microfluidics, microvalves that really revolutionized applications in microfluidics, biology, chemistry, and so on and so forth. I took this out of this very interesting paper out of Quake's group at Stanford, where effectively did valves by using flexible materials like polymers, and by increasing the pressure in one channel, the channels are in crosses. You can squeeze the channel below and close it by squeezing. So the principle, it's not that much different than the Romans, right? It's simply a mechanical valve. The beauty of this is that with the materials that were used and the technologies they used to fabricate channels, you can put thousands of these valves on chip. Okay? So then it is a very useful development in the area of technology, but again, the physics is the same, in my view. The objects we're dealing with require different physics because we have to deal, when you deal with nano objects, with Brownian motion, thermal motion. And as you can see from this sort of rough graph, that is a distance traveled by an object, let's say within 1 second, as a function of diameter. Those things jump around if they're in the size of, let's say, 40, 50 to 100 nanometer diameter, within 1 second, about 100 diameters. And if they're smaller, like it's 1 nanometer, and this is a log graph, the travel will be a few tens of thousands of diameters. So you're dealing with these things that move up and down, left and right, and jumping. And if you want to control them in the individual nano level, it's impossible to do it with some mechanical means. So find them with some kind of mechanical device and move them around. So our concept is a bit different, the physics in our concept. So we decided to use electric fields and actually use the collaborative effects because we want to do, by the way, I forgot this, the challenge is to do that on chip, with an on-chip technology. Not simply to do like an optical trap and get one and move it around. Right? On-chip technology. The challenge, it works the combination of external electric fields with these nanoelectrodes that you see here, and topography. And we hope that by dealing with these electric fields, the external ones, the inherent ones in all these water aqueous solutions that we have that contain ions, all right? The so-called electric double layers. And the topography combination, we will be able to control the motion of these particles. And the first step in that direction is not that complicated. I mean, it is complicated in fabrication, and all this work that you put in the supplementary information is like years of work in the clean room to do this device at the beginning. Then you have, of course, a protocol, and you can do it in a week. All right? But if you see here, you have a cartoon of the electric double layers. In water, typically, this would be 50 to 100 nanometers. And if you have a device that is, let's say, from here to there, a couple hundred nanometers, then you have an electric field in between, so that if you have a particle that on its outer surface has an equal charge, okay, and that happens mostly naturally, then of course this particle is being repelled by this electric, it cannot go through, okay? So if this is like a valve, now the valve is closed. As you can see down here, these are real experiments. By the way, to see and do these experiments it's far from trivial. We use interference scattering for this for nanoparticles or fluorescence later on. That's rather complicated. So it knocks on the door, but it cannot go through. By now applying an electric field through your nanoelectrodes, then you open the valve, and you can think this of force or of changing the energy landscape. Okay? And then you roll it down the energy landscape, and that particle goes through. And you can see it here in terms of real experiments. If you have one of those on the other side, and it's closed, you can close both of them and keep it in between. Okay? And of course, then you can start thinking about devices. You can put those several in a series, and then you can do this kind of devices where you have sorting and capabilities in this Y kind of device that you've seen in microfluidics is similar, but only nanofluidics. Typical dimensions here would be like about 400 nanometers cross-section, and where the stenosis is a couple of hundred nanometers. So all that can be done with standard lithography technologies. And then, of course, you can have your containers here, your little tanks with your liquids, your particles, and so on and so forth. You see that the electrodes here in a non-chip sort of design. And what you see here in between are the valves. Okay? So you can start doing experiments with this principle. And I'm going to show you a video of this. Since I came to India, I figure let me show them a few very kind of cool videos. So we see now there is no bioparticle, and this is water. It's a gold nanoparticle that allows us to measure it with scattering. Interference scattering is a technique that we use that can be manipulated like this. So this is the real data, and that is an SEM that we took, and upon which we were able to then record the position of the particle for clarity. So here you have all valves are closed, and you have 3. Okay, this thing is moving by thermal motion. You open this valve, it goes through. You can close the valve. You can do whatever you want with it, and then you can let it go on the other side. And you can see the potentials here of the electrodes. You can bring it back if you want, if you made a mistake. All right? You can then put it on the other channel. You can bring it back again. You can even send it backward. So we have very good control of the single nanoparticle. And we can see it pretty well, actually, because interference scattering for metals works very well. OK, good. So, but we were not done with that, because our goal was not to only do particles, but to work with biological solutions. And now you start seeing the challenge of the biological solutions. OK, distilled water has a very low ionic strength, less than 0.5 millimolars. When you go to, so the corresponding double layer thickness is about 50 to 100 nanometers. As you saw, you can do the topography with standard lithography. Things will work. Now, in biology, we have very high ionic strength, 2 to 3 orders of magnitude higher. And if you look at the sort of Debye length, that gives you the order of magnitude of the electric double layer, it's inversely proportional to the ionic concentration. And then all of a sudden, your double layer is very small. It's 5 to, let's say, 10 nanometers. So if I try to do my previous game, it's not going to work. Because I don't have this, this barrier anymore. So I have to do something else. So preferably, and on these discussions, I mean, this took a few years, right, to do. We wanted to keep the same device. Because you made this device. Let's see if we can keep the same device and work a little more cleverly with electric fields and see who can do the manipulation like that. So, so we decided to use AC electrokinetics, okay, to do this. And I'm going to skip to this slide. I'm going to discuss it very briefly. Also, AC dielectrophoresis. If you're not familiar with dielectrophoresis, I do recommend this very nice book that explains the physics behind this. But the bottom line here is that, of course, your particle and the liquid have different electrical properties. They have different electrical permittivities and conductivities. If you put them on an AC field, those charges move around. And if you play your cards right, so to speak, frequency-wise, and for our work, it's about 10 megahertz frequency, you can generate an energy landscape or generate a force on the particle, a net force, that now acts as a brake, if you think of a force. Or if you want to think of this of energy, you basically amplify the energy barrier, and the particle cannot go through. You'll see that in a second. 2 words about these little equations here. That would be sort of the interaction energy landscape. The derivative of this would be a force, let's say. It's a function of the size of particle. If it's a sphere, it goes with a cube. So if I can do something for 100 nanometers, and you tell me, can you do that now for 1 nanometer? My field has gone down 1,000,000 times because of this. And there's nothing I can do to basically correct for this, to strengthen the energy, except for this, okay? The electric field. The electric field, as you'll see in the next slide, I think I'm saying it, can be amplified by the nanotopography. And of course, we have the square electric field there, and I can capture most of what I lose by going down in the size. So the two together will allow us then to basically go smaller in size, toward to 10, a few nanometers. Okay? And so we did all that. Again, same device. So basically, different kind of electric fields. And this time, instead of the energy landscape pushing it through, this time the energy landscape holds it back. Because if you do nothing, it'll go through. So, and then let me show you maybe some results here. Here's a virus, about 80 to 100 nanometer size. I mean, you're familiar with these pictures now because of the COVID virus, right? And the spike proteins and so on and so forth. But this is not a COVID virus. This is an adenovirus. It's effectively, in the lab, relatively harmless, unless you are immunosuppressive, in which case you might generate some problems. So you have to do this in a certified bio lab. And indeed, as you'll see here, by using the approach that I showed you before, we elevate the energy barrier here, and we're holding it back. It doesn't go through anymore. Okay, the valve is closed. And indeed, for the adenovirus, we were able then to close, open, trap it, do whatever we want. So I could show you a film on that, doing the same thing now with a really biological fluid with a very high ionic concentration and with a biological nanoparticle. And that is when, of course, the student who did this PhD thesis, the very good student that did this thesis, Chandra can work very hard for this because I can present it now in 20 minutes, but this took like 4 years, all right? So ran out of gas. And I couldn't do what I really wanted, which is the molecule, right? So a new student came. And his job is to basically step on the shoulders of the previous students. And in the first part of his thesis, because he had 2 parts, finished the job by looking at the biomolecule, and we selected this immunoglobulin molecule. It looks like a little lobster, but it's a very small one. It's about 8 nanometers in diameter. It's the most common antibody in the human body. 75% of our antibodies are of that kind, and so on and so forth. So you see here where the 2 latches where effectively the antigens binding takes place, and so on. For us, it's just a particle. Now, I did indicate already to you the challenge. Okay, I'm going, let's say, from 100 nanometers to a few nanometers. Let's call it 10 nanometers. We do not want it. This is about 8 nanometers. And from the previous equation, I lose the strength of the electric field 1,000 times, more than 1,000 times. There it is. Okay. Now, the thing with the electric field, in addition to that, so let's say it's 10 nanometers. I lose 3 orders of magnitude here. And of course, the diffusivity increases. Also, because it is inversely proportional to the diameter, and of course, that's going to be 10 times higher. Let's call it 10 to the 4th, right, to have a round number. And of course, what you have is the electric field and the topography. This is my previous topography, denoted by L. Okay, so the only thing I could do, but if you have other suggestions, I would be happy to, is to basically, on top of the previous topography, put a stenosis. And this is exactly what we did. So you have this previous topography, and on top of this, we have a stenosis, W. And you can see this as fluids people as a continuity equation. Electric field times cross-section is the same on the two. You take the electric field and you squeeze it through the stenosis, all right? And if you solve this for the electric field in the stenosis, in the W, and this is an order of 10 less, then you recover the 10 to the fourth. So as far as energies, you're pretty much where you were, and you hope that you will be able to hold this particle. And this is an SEM of the device. If you look real carefully here, you see the little stenosis right there, in addition to the cartoon. So this is difficult to see, of course, because we can see it with fluorescence. But here you will see the motion of a single molecule, that molecule that I showed you before, sorry. Same story again. We can see it fluorescing. Of course, there are statistics here, obviously. Okay, and you do the same thing. Valves are closed. Silence in the room. This thing is moving. Open the valve. We trap it in the valve. It stays there. You can calculate also the time of residence based on the probability density function of this. And then we can open, stand to the left and the right, and do the same story like before. So we did it. We're happy. We put it all together, and we published the paper. So that is where the road has led us, the first step at least. We did a lot of particles. Now you see here, in terms of ionic concentrations, where the DC mode works, the easier stuff, and where the more complex AC mode works. And most of biological nanoparticles, we tried lipid vesicles, adenoviruses, quantum dots that are nice because you can see them easier, okay, and so on and so forth. So then in addition to that, now we've trapped them where we were in this work, and with the piece of work, we try to characterize them. In the trap particle, can you calculate its conductivity and these properties? And we did this actually for the adenovirus, and we were able to do that. But that is based on the kinetics then in the trap. Now, typically, how tight is the trap? Roughly speaking, on the average, the motion is now, instead of, I don't know how many diameters, within one diameter. So it still vibrates a little bit, but the trap is very tight. Okay. So, second part of the talk. So the similar goal, single molecule, we're almost obsessed with single molecule manipulation, right? But this time by printing. And now here we were a lot more comfortable because we knew a lot more, worked on this for many years, and basically we used the combination of electric fields and interfacial energy of the liquids in terms of electrohydrodynamic printing. A few words on its physics. So if you have a nozzle with a liquid with some ions in there, and just all useful liquids have ions, not all, many, but certainly all the liquids that carry particles in them, organic particles, inorganic particles, or whatever, there are ions in these solutions. So you don't need to add any ions, right? And you put an electric field across here. Then, of course, you have electric stresses that apply on the meniscus. And the meniscus can be deformed and also removed from the nozzle. And in this nice review paper, the various modes are discussed, where effectively, if you have a nozzle like this, and you see now a little bit of electric stresses, of course, the surface tension force would be resisting this deformation. So it's an interplay between the two, effectively, right? So electric stresses and surface tension, you can just pull out the whole thing, all right, from there, and you have this dripping mode. Right? Or if you increase the voltage, you can start, before dropping it, sharpen it. You start sharpening it to the point where it's extremely sharp, and that is a Taylor cone mode. You have a cone, and you're shooting a jet, actually, at the end of that cone. And that jet is very thin. It could be down to like 10, 20 nanometers. And by Rayleigh instabilities, it will break up into droplets. So you have a stream of droplets, very small droplets, charged equally, traveling through space. Right? And of course, this does not have to be done to go that far. You can stop earlier before you go all the way to the cone and have a dripping, but now the dripping is completely different. And this is the mode that we used, right? But at a nanoscale. We were able to, it was realized at the micro scale, but we realized at the nanoscale. So you effectively stretch it, but every time you print not the whole thing, but the apex of the stretch part, which is not fully a cone yet. So this is the regime that we developed at the nanoscale, and I will tell you why this is an advantage. Over the cone, and of course this can go unstable, and then you have things like that, and you have multi-jet modes and so on and so forth. To print, of course, with the precision we want, you don't want any lateral movement. That's clear, right? So effectively, the nano dripping or micro dripping, since you print something that's much smaller, a good order of magnitude smaller than the opening, it helps also with respect to clogging, because we have particles in solvents here, and those vaporize. 5 minutes left, no problem. Those vaporize, and of course you can have easily clogging. So this avoids clogging. And the Taylor cone jet, which would be a nice approach, the problem that it has is that you have a lot of droplets. You shoot in them, plus, and that's some people don't see it directly. Those droplets are equally charged, so they repel each other. So you can never focus it down to the single droplet. They go like this. So I think that's the thing. So when you see Taylor jet nanostructures, they're actually microstructures. They call them nanostructures in the paper, but if you look at the size, it's never a nanostructure. It's a microstructure. So our approach then, if I cartoon it, it looks like this. We can print anything pretty much. The last very exciting work that we did is we basically printed reactive ions. So we didn't have any particles there. So we're generating ions in an electric field that would generate particles. But we'll come back to, I will not talk about that today. So we used rather large nozzles of a few microns, which we pulled. Of course, you have to have conductive materials here and there. You don't have to have a conductive material here because you can put one under where you want to print. So the distances are important, of course. Typical distances now are rather small in this technology, 3 to 10 microns between this and that. And then you have, of course, in our technology, one drop at a time between nozzle substrate. Before the next drop comes, the first one has vaporized. So effectively, you can focus it. And the other thing when you hear dripping, I want to say this, oh, dripping, it's such a slow process. We can go up to 30, 40,000 droplets per second on this, with this technology, right? And the voltages, because you have these droplets, people tend to think that it's an AC voltage. You could play games with an AC voltage, but a DC voltage is enough, because effectively all you have to do is stretch it, and then it shoots by itself, effectively. So then the cartoon version of what's happening is here. And then, of course, you can build up. And other features of this, because the physics is actually very, very rich, these are very small droplets. Imagine this droplet being like 30, 40, 50 nanometers. The mean free path in air is the same. So basically, they travel in pretty much vacuum, partial vacuum, right? Then they have no weight. There is no way you can deposit this by gravity or there's no inertia, because the mass is zero, effectively, very small, right? So only the electric field, because they're charged, can take it and accelerate them, and they hit with high velocities. But because they're so small, the Reynolds number is less than 10. So therefore, they act very viscous, so they stay together. That's the first thing I want to discuss. Now, what happens at the bottom? Initially, you might think you don't want it to wet. No. You really want the solvent to wet very well, because what happens is it wets and vaporizes very fast, but the particles, because of van der Waals forces that you have in your solution, stick themselves on the surface. And they're not carried away to this coffee stain sort of geometry that maybe you've seen in other kind of studies. All right? So effectively, you can go ahead and continue. And you actually you can build structures. The first piece of work we published, it's about 10 years ago on this, says what I told you, and you see that's 150 nanometers scale. That's about 80 nanometers. And you can see how this is built up. You can do columns, and it turns out these materials were very interested in optical applications, and I'm going to come to that in a second. Actually, I'm coming to that right now. Okay? So we've done a lot with this. Of course, we've got a lot of collaborations doing this and that and the other from electrodes and so on and so forth. I forgot to talk about this autofocusing effect. This is very important. The autofocusing effect is this. Once you start building this up, the next droplets that come are attracted by this. It's like a lightning rod effect. So effectively, it's kind of stable. You can go up pretty high. Okay? Don't want to forget this. So then you can print quantum dots, because we got involved with our friends in nano-optics. So, and this is 100 nanometers. You can see the capability. You can go down to about half the size pretty easily. Many applications. I'm going to show you one here because I'm talking about biological particles. Now you can go ahead and print all these quantum dot disks on a polymer upon which cells can live. So you print this matrix of quantum dots on this polymer substrate, hydrogels as well, by the way. Then you put the cells on there, and the cells move. And of course, when the cells move, the substrate moves. And it moves in 2 dimensions, but also in 3 dimensions. And if you know the constitutive equations of the polymer, or whatever you have under there, you can then, from the deformations, you can back out eventually stresses. So you can measure forces and stresses with unprecedented resolution with this technology. So that has led to a lot of collaborations with biologists. Of course, we had our fun, too. So you can print color pictures. These are the smallest, as this is official in the, this one, another one with little fish in the Guinness Book of Records, all right? This is the smallest color picture ever printed. So this is from a poster. Well, this poster is like 50 centimeters by, 30 centimeters, something like that. And this scale is 20 microns, and it's colored. And how do we print this? By mixing quantum dots and then looking at the RGB spectrum and mixing colors, of course, so that through interaction of colors, you generate colors. Well, this is a nano parrot. You can see the printing details here. You can see the eye here, if you want, of the parrot. So we had our fun with that. Last slide, 2 slides. Okay? And then molecule, all right? So basically, we want to print molecules. It's not easy to print a molecule, I guarantee you that. But it turns out that printing single molecules, placing single molecules at precise locations, very close to waveguides and so on and so forth, is very important in optics because single molecules, organic molecules like this one, clearly dye, they are single photon emitters. So effectively, you can have single photons emitted in waveguides. That's a very interesting research problem in nano-optics. Or you can put 2. Can we put 2 near couple it to the nanoguide? So effectively, you have to be able to place these molecules very close to the nanoguide. And one of the state-of-the-art techniques is statistical. Just throw a bunch of molecules there and see what's close to your nanoguide. The guide, this was actually from the Nobel lecture of Murner, who effectively has done tremendous work from the standpoint of optics in this area. So then we use our technique, and we're able to print then individual molecules in their host, okay? Because the molecules have to be in a host crystal, and we have then our nanodroplets, each one containing 1 molecule or 2 molecules, and so on and so forth. And we're able to demonstrate this, as you see here. I'm going to start with this boring picture that shows you stochastic, just throw them down, right, versus our method, okay? So if you want 1, this is percent. If you want 1 molecule near your nanostructure, statistically, with the stochastic, you have about 1%. With us, you have about 90%. But if you want 2 molecules or 3 molecules in the same area coupled with a nanoguide, of course, let's say 3, stochastic is 10 to the minus 4%. And we are 30%. So there's a huge difference. So, and with that, I'd like to close my talk. It was 7.5 minutes, right? Not 5 minutes. Thank you for your attention.
When you are using the square wave actuation, so what frequency did you decide? Square wave actuation, what you are using for the AC spray.
For the valve, right?
Yeah.
For the AC, it's about 10 megahertz. So 10 megahertz.
10 megahertz. So how did you decide that one?
Oh, you see, the force, you can look at the landscape, the force could be pushing in one direction or the other direction. It's a function of the frequency because of the way the electrical properties work. So if you go a little bit above, close to 10 megahertz, then you pull the brake on the particle.
Okay.
And that you can look so theoretically. Because this value of this, okay, let's show the equation. For example, this equation, right? This CO, I didn't discuss this, which is a function of frequency, and it's a function of the complex conductivities of the particle and the medium. I mean, no time to discuss this, yeah? And also this is, of course, inside this you have the electrical permittivity as well. This, for our, it can take this range. For us, it has to be negative to pull the brake. Okay. So that, of course, decides to you the range of frequencies where you have to work.
And just one more question, the nozzle you have taken it in micrometer size.
What?
Nozzle diameter you have taken micrometer. So why did you go for micrometer? That Taylor cone, does it affect?
In this problem again?
Yeah.
What diameter is this?
The diameter I saw some micrometer.
Was it 0.1 micrometers?
Yeah, something like that.
If it's 0.1, it's nanometers. Yeah.
Yeah, maybe it is 2.
Where?
Yeah.
Let's see. Here? I don't know.
The second part, yeah.
Oh, the second part?
Yeah.
Oh, the second part.
Second part.
Yeah.
Yeah, I think.
Well, I will come to that.
Yes, you can.
I have time. I mean, you don't have time. I have time. Second part.
Yes, here. That the printed nozzle is 1 to 2 micron.
Oh, 1 to 2 microns is the thickness of the coating here. Let's see. It's the thickness of the coating. Oh, no. So I'm sorry. 1 to 2 microns is the diameter of the nozzle.
Diameter, yeah. So what is the reason?
Oh, how do I do this?
Yeah. Now, why did you take 2 micrometer?
Why?
Yeah.
Well, I want to do it as big as possible. If we could do it 1 meter, it would be easier. All right? So, but I want to print as small as possible. All right? So effectively, so I have to pull it from what the diameter tells me to what I want to print. If I'm around 50 to 100 nanometers, all right, and I can do it in the nano dripping regime with about an order of magnitude higher diameter. So that's what decides. I can go bigger, but I'm going to print bigger. I can go smaller, and I can print smaller, but I might clog, because these things vaporize. Then you have to add an environment that blocks vaporization, and you can go crazy. I mean, you can do a lot with this, but I'm showing you here just the principle, all right? Okay?
Thank you.
Yeah.
So thank you for a beautiful talk. And in the beginning of where you showed nanoparticle valving, you are using DC fields to control the system, right? Turning on and off.
The nanoparticle?
Yeah.
Yeah, a DC.
And so my question is, the transport of particle, is it only Brownian motion driven, or do you also have electrokinetic transport?
Yeah, right. So the kinetic flows for this are very weak, okay? We do vaporize on one side, so you pull it a little bit, but really it's the Brownian motion that dominates in that.
I had one question, Professor. So you use this, I think, SiO2 surface for printing it. So if we use some other kind of surface, like polymeric surfaces, will the print be similar?
I didn't get it, but you're talking about the glass slide?
Yes.
Here?
If we change the surface, how will the print get affected?
I couldn't care less about it. I could use any surface. The only thing that's going to affect is the wetting properties. Very important, because effectively, remember, for this to work at the focus level of the particles, if you carry particles, you have to wet well. So if it's, I wouldn't use a super hydrophobic surface there, but, or you can treat a surface very easily to make it philic. Most of these solutions come with, the solvent is a hydrocarbon, and they wet just about everything well.